A voice agent can feel slow, even when the LLM is fast. LiveKit metrics and OpenTelemetry will split each turn into STT, model, and TTS delays so you fix the real bottleneck. You'll see how to connect the pieces into a workflow that traces each voice turn and flags the slowest stage against latency budgets. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Latency in voice agents is more of a systems problem than a model problem. Users judge the whole turn, from their speech to the reply they hear, not just one component. So, we need stage-level timing, not only end-to-end numbers. Teams that only watch overall latency often chase the wrong thing because they don't see which stage actually caused the delay. If you can point to STT, the LLM, or TTS, you can fix the slow part and stop wasting effort on the pieces that are already fast. Think of a single spoken interaction as 3 timed handoffs: user speech, transcription, model computation, and finally, synthesis. We capture timings at each handoff and then compare percentiles so tail behavior shows up. The payoff is focused remediation. The downside is you must reliably correlate events across metric streams with a shared ID. We'll build a compact diagnostic pipeline that listens for LiveKit turn events, wires per stage metrics, computes median and tail budgets, and writes the diagnosis into OpenTelemetry traces for postmortem. It's not production plumbing, but it demonstrates the core moves that make stage diagnosis actionable. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we capture the basic end-to-end signal so we know when an assistant turn finished and how long the whole response took. This snippet listens for completed assistant turns and prints LiveKit end-to-end latency. End-to-end latency is the first number most teams watch, but by itself it does not explain where time was spent. The LiveKit session on conversation item added hook gives you each chat message, and EV item metrics get E2E latency reads the per turn value only when the assistant actually responded. That keeps proactive messages and incomplete metrics from polluting the signal. The visible output shows the turn level response delay, which becomes the baseline you will break apart next. Now that we see whole turn times, we need to collect per stage metrics from the services that actually own latency. This example subscribes to LiveKit component metrics and stores stage timings by turn. A slow voice turn often has 3 different owners, so the code attaches pipe-on metrics collected collect to session.stt, session.llm, and session.tts instead of treating the session as one blob. The collect function uses speech ID to correlate events that belong to the same spoken user turn. Here, EOU metrics.transcription delay represents the STT side delay, while LLM metrics.ttft and TTS metrics.ttfb capture first token and first audio timing. The output confirms that 3 LiveKit metric streams are wired into the same turn store, with per turn stage timings. The next need is synthesis into actionable budgets, and a simple rule for what to optimize first. This code turns collected LiveKit stage events into P50 and P95 latency budgets. 1 or 2 bad turns can hide in an average, so the PCT helper sorts each stage and reads a percentile instead. The complete list keeps only turns that have STT, LLM, and TTS measurements, which avoids comparing partial records during incident review. Then budget stores both the median and tail value for every stage, and slow selects the stage with the largest P95. The output shows which stage owns the current tail latency. So optimization starts with evidence instead of guesses. Numbers are helpful, but traces put those numbers into the timeline for deeper debugging. The next step is to wire OpenTelemetry into the session so spans carry context through the call. This snippet configures LiveKit agents to send spans through OpenTelemetry. Metrics tell you the numbers, but traces give those numbers a place in the request timeline when you are debugging a real call. The code creates an OpenTelemetry tracer provider, adds a simple span processor with console span exporter, and passes that provider into LiveKit with set tracer provider. In production, the exporter can point at an OTLP-compatible backend, but the local console exporter keeps the tutorial visible and minimal. The output shows that an OpenTelemetry tracer is ready before the LiveKit session starts. Finally, we want a durable trace that records which stage we flagged as slow and why, so ops can inspect the decision in context. This example records the latency diagnosis as an OpenTelemetry span you can inspect later. During an incident, it is not enough to know that one turn was slow. You want the trace to carry the stage budgets that explain the decision. The code uses tracer.start as current span, voice turn.latency. Write slow, every P95 budget, and the number of complete LiveKit turns as span attributes, then calls provider.forceFlush. That makes the measurement durable before shutdown or deployment restarts. The output shows the stage selected for attention and confirms that all 3 budgets were traced. In a real project, you would point the exporter at your observability backend and attach spans to real request IDs. This lets alerting use the same trace IDs that engineers open in their tooling, and it makes post-incident measurement honest. 3 quick takeaways. This pipeline captures whole turn latencies, enriches each turn with STT, LLM, and TTS timings, and ranks stages by tail latency, so you know where to focus. Use it when you need to stop guessing which component causes slow voice responses, especially when the tail matters more than the median. One caveat: you must correlate events reliably, so instrumenting a stable speech ID or request ID is essential. A practical next step is to tune the P95 budget you compute for each stage and run the pipeline on a set of recorded calls. Lowering the P95 target for the stage that owns the tail will show whether configuration, model choices, or resource changes shift stage ownership in practice. If practical AI engineering helps, subscribe and watch the AI engineering videos.